Ladder diagram, or LD, is one of the most widely used programming languages in industrial automation. It is a graphical language designed to mimic electrical relay schematics, making it intuitive for electricians and maintenance personnel to troubleshoot. In this video, we will go over the basics of the ladder diagram language. We will create a ladder logic project in CoDeSys and simulate it in our virtual PLC. We will explore the specific tools within the editor and implement the fundamental building blocks of the control logic, contacts and coils. It is important to emphasize that while we are using CoDeSys for this demonstration, the principles of LD are universal. Whether you're programming a Rockwell Automation control logic using Studio 5000 or a Siemens S7 using TIA Portal, the logic symbols and execution rules you learn here are directly transferable. If you don't have CoDeSys installed in your system or you don't know your way around it, check out my series of videos for an introduction to CoDeSys, links in the description. Let's begin by setting up the environment. Open CoDeSys and let's create a standard project by clicking on File, New Project, and let's select a name for the project. Here I will call it Intro to Ladder Diagram and click OK. After a while, CoDeSys will prompt you to select the device and the language for your main program. The device doesn't really matter because we will use a simulation mode, and for what concerns the programming language, let's select ladder logic diagram. Note that when you want to use ladder logic in your program, always select ladder logic diagram and not ladder diagram, because the ladder logic diagram in CoDeSys is much more complete, as more tools is actually a better implementation of the ladder diagram language, while the ladder diagram here, this one, is a, let's say, legacy option in CoDeSys that is maintained to maintain backward compatibility to older project. For newer project, you should always use ladder logic diagram. Let's click OK, and CoDeSys will create your project. And in the newly created device tree in CoDeSys, you will see a PLC_PRG program created for you that will be implemented using ladder logic diagram. By double-clicking on it, we will be able to interact with the program. We can edit the declaration part and the implementation. Now, before moving on, let's explore what the editor provides us. In the top part, you will see the program declaration. This is the same on all programming languages. Here you can define the variables related to this program organization unit called PLC_PRG. On the bottom part is the implementation part, that is where the actual ladder logic will be written and will be placed. On the right side, we have a toolbox to place some useful operator for ladder logic in our program. And in the top part, when you click on a network, here we have only one for starting, you will see a bunch of other buttons that are again useful operators that can be used to place all kinds of contacts and coils or other objects that are necessary for our program. Before moving on to the practice, let's focus on the fundamentals of the ladder logic language. Ladder is a language that is based on dividing a program into rungs or networks. You can create new rungs by right-clicking anywhere in your program and clicking Insert Network, and you can see that you will have multiple numbered networks over there on the left side. Each network or rung acts as a single line of code and all rungs are executed sequentially from top to bottom at every scan cycle. They act in the same way as lines of code in a textual programming language. The core concept in LD is power flow. Logic on a rung is evaluated from left to right. Ladder is based on having two vertical lines known as power rails. Actually, in CoDeSys you see only one, the one on the left, and you can think of that as a live or hot power source, like a 24-volt power source or an L1, something in which there is power. And on the left side you will place, on the left side of each rung, you will place some input elements, some conditions, a logical path that will either allow power to flow or it will stop it. All this according to the conditions that you place in your code. Then on each rung there must be on the right side some kind of output element. Typically output elements are known as coils, but you should know that they are something that if power flows to them, they will do something. Now let's remove the extra networks that we have created in our program by clicking on one and pressing the delete button. Since we will work with only one for this example, and let's create some variables that we will use for our program. Let's assume to have an input variable that we want to evaluate and an output variable that we want to set. So I will create a first input variable that I will call switch A. That will be a Boolean variable, and an output variable that I will call light B. That will be again a Boolean variable. Now let's create some contact to evaluate the value of our input variable. To add contacts to your program, you can do it in two ways. Either right-click on a network and press Insert Contact, or by clicking again on a network, you can click on in the top left part of your screen into the Insert Contact button. By doing this, we will have created what is known as a normally open contact in our rung. A normally open contact is an element that will allow power to flow from left to right if the associated Boolean variable is true, and it will block the power flow if the variable is false. The normally open contact or NO contact is also known as XIC, examine if closed. And when you place a normally open contact in CoDeSys, you will see those three red question marks on top of that. And this is where you place the variable that needs to be examined. And before you place any, you will see the three question marks. So let's associate our switch A to the normally open contact. Right now, this switch isn't actually doing anything, because even if it's allowing or stopping the power flow, on the right side of it there is nothing, so power flow won't do anything. We need some output element to actually do something with this power flow, and output elements that are associated with Boolean variables are known as coils. To add coils to a network, you can do it in two ways: by right-clicking on a network and selecting Insert Coil, or again by clicking on the network and using the Insert Coil button on the top left part of the CoDeSys editor. And by doing it like this, you can see on the right part of your screen, you will see this element. This is a coil, again with 3 question marks because there is no variable associated with it. And how does a coil work? If power flows to it, the associated variable will be set to true. If power doesn't flow to it, the associated variable will be set to false. Let's associate our light B variable to this coil. So what will this program do? If the switch is pressed, power will flow and the light will turn on. If the switch is not pressed, the power flow will be blocked here and the light will be turned off. We are actually setting the value of the light to be equal to the value of the switch. So let's test this program in simulation mode. To do that, first click on Online, select Simulation to allow simulation mode. You will see it in the bottom right part of the screen that you have enabled simulation mode, and then log in on your simulated PLC. If this is the first time we are starting the simulated PLC in a while, it will tell you that the application does not exist and you can download it. Then you need to set the PLC in run mode by clicking the start button on top. And here we are actually able to visualize the power flow in ladder logic. You can see on the left side we have the live power rail. The blue means that the power is flowing and it gets to the switch and it is stopped there. And it doesn't reach the light. And you can see that in the online value of the variable. Switch is set to false and light is set to false. Now let's try to do some change. If we change the value of the switch, you will see the light turning on, and to do that you need to click here on prepare value, and to set the value of your variable you need to press Ctrl Fn F7 or Ctrl F7, and you can see if we set the switch to true, the light becomes true because the power is flowing to the switch is allowing power to flow, and the power is reaching the coil. And if power reaches the coil, the associated variable becomes true. Now doing the opposite, let's set the value to false. You can see that the light turns back to false. This program, as I said, is actually setting the value of the light to the value of the switch. Now let's log out and see how to do the opposite, how to set the value of the light to the inverse of the value of the switch. To do that, we can use a normally closed contact instead of a normally open one. A normally closed contact will allow power to flow when the associated Boolean variable is false, and it will block the power flow when the variable is true. To add a normally closed contact, you can either right-click and select Insert Negated Contact, or again use the bottom on the top left part to insert the negated contact. Or if you already have a normally open contact and you want to turn it into a normally closed one, you can right-click on it and select Negation. This will turn the normally open one into a normally closed one. And you can see that the symbol is different. This is the symbol for the normally closed contact. It is also known as an XIO, examine if open. And it will do what I just said. So let's go back online and let's carry out a download and start the PLC. And as soon as we start the PLC, you can already see that switch A is false and light B is becoming true, because the power is flowing through here because switch A is false. If again we set the switch A value to true, you will see that the power stops over here. And this works in the exact opposite way of the program that we've seen before. We are setting the light to the opposite value of the switch. This simple interaction, power flow moving through contacts to energize coils, is the foundation of all ball and ladder logic. Even the most complex machine safety interlocks or the most complex process implementation are built upon this basic feature. If you want a textbook by your desk to follow along and to know all the basics of ladder diagram, check out my book PLC Programming for Beginners on Amazon, or check out my course PLC Programming Learn the Basics with CoDeSys.